States of matter, part 2. Ideal and real gases. Previously, in our earlier PowerPoint notes, States of Matter Part 1, students learned many things about the states of matter and the phases of matter. And in particular, we explored mathematical relationships that exist between properties of gases. These were discovered by early scientists of the Enlightenment era, people like Robert Boyle, Jacques Charles, Joseph Louis Gay-Lussac. This was in the Enlightenment era, which is roughly between 1650 and 1800. And these mathematical relationships discovered by these pioneering chemists are often called the gas laws. Students learned, for example, that the product of pressure and volume is a constant, where P1 V1 equals P2. This law, Boyle's law, is an inverse relationship that leads to a curve. It's an inverse relationship because one property increases, moving towards infinity, while the other decreases, moving towards zero. Students also learned about Charles' law and Gay-Lussac's law. These, in turn, demonstrate a different relationship, which is direct and linear, between either volume and temperature, as in Charles' law, or pressure and temperature, as in Gay-Lussac's law. They both have the same form, and in those, if one property increases, the other increases, and if one property decreases, the other does the same. Now, these three simple laws can all be collected together in what's called the compound gas law, or sometimes it's called the combined gas law, precisely because it combines those three simple laws into a single expression. If you look at this formula, P1 V1 over T1 equals P2 V2 over T2, if we imagined that there was no fraction and that there were no T's, then that P1 V1 equals P2 V2, that would just be Boyle's law. Or if we imagined that the pressure term was not there, that would be Charles' law. Or if we imagined that the volume term was not there, that would be Gay-Lussac's law. We have this handy graphic with V, P, and T, representing, of course, volume, pressure, and temperature. And they all have arrows going back and forth from each one. What that means is that they all influence each other. If you change the pressure, that changes the volume, which changes the temperature, which changes the pressure, and so on and so forth. Our early scientists who developed these gas laws actually had to do some pretty careful experiments to see the patterns, precisely because it was difficult for them to control for one factor while looking at just two. Nevertheless, you can combine them in three, and we could do problems where instead of having three known variables and one unknown, we could have five knowns and solve for one unknown: pressure, volume, and temperature. But that's getting kind of complicated, and there's a much easier way, much more useful way to solve more complicated problems like this. Now, the reason why it's going to be more useful is because all of our gas laws to this point, Boyle's law, Charles' law, Gay-Lussac's law, and also this compound gas law, they are dealing with the pressure, volume, and temperature of an enclosed gas. That is, we assume that the amount of the gas itself does not change. You have some kind of closed system, no gas gets in, no gas gets out. And so these are kind of artificial situations, really, that are, usually only approximated in a laboratory. And so the calculations we get for any of the simple gas laws, it only allows you to work in those situations when the amount of the gas is a constant. But in the real world, for example, like our own atmosphere, it's not really a closed system. And while pressure, volume, and temperature might all affect one another, another thing that affects what's going on, in fact, the primary thing, is just how many particles are actually present. And are the number of particles constant, or are they changing? So for these situations, we use what's called the ideal gas law. PV equals nRT. Now, of course, P is pressure, V is volume, and T is temperature. But what is lowercase n? What is capital R? Well, we'll get to that. We use the ideal gas law in those cases where the amount of a gas is either unknown or else not constant. We use a term N to refer to the number of moles. We'll use the number of moles to keep track of the amount of the gas. And we're actually adding this term to the compound gas law that we just introduced. So again, we have P1 V1 over T1. Well, we're going to add a term on the bottom that says lowercase n1. And that simply refers to the number of moles before, and lowercase n2 refers to the number of moles afterwards. And so this term, the addition of this term, makes it possible in principle to compare the number of moles before and after. Now, what about R? Well, R is a constant that has been fiddled with, and it can have different values. But the key thing about R is that it actually not only includes a number for pressure, volume, temperature, and the number of moles, but it also includes a unit. And so R actually, in a sense, equals pressure times volume divided by the number of moles times the temperature. Now, what value are we going to get for R? Well, it depends upon the unit that we choose for pressure and also maybe if we're going to use Kelvin or Celsius for our temperature. If we choose the unit of the atmosphere, that can make math convenient because we can just talk about one atmosphere. But different values are also possible if we have other units or if we have them at any particular temperature and pressure. In practice, we try to simplify all these problems by calculating a value based upon standard temperature and pressure. And for that, we use atmospheres, liters, moles, and Kelvin. And so this region highlighted in green kind of explains what's going on in one particular situation with R. If we say R equals PV over NT, okay, one really simplified way of doing that in terms of units is that we can use 1 atmosphere for the pressure because that's the standard pressure at STP. And we can use 273 Kelvin for the temperature because that's the standard temperature at STP. And it turns out that if you have 1 mole of any gas at these conditions, that is said to be the molar volume, which is 22.4 liters at STP. And so in this formula, this makes the math pretty simple. Really, it's 1 atmosphere times 22.4 liters divided by 1 mole times 273 Kelvin. Now, if we happen to choose those units and those particular values at STP, we come upon a useful number. That number is 0.082. Again, when R, the ideal gas constant, is based on units of atmosphere liters, moles Kelvin, then its value is 0.082 at STP. And I need my students to memorize this number to solve ideal gas law problems. Now, what if you're given a problem where the pressure is not atmospheres, or maybe even the temperature is not Kelvin? Well, if that's the case, R might have different values. And you can see some examples of those different values there. However, in this course, the only number I want you to memorize is 0.082 for atmosphere liters moles Kelvin. And if we ever use a different value, well, I'll tell you in the problem what it is. You won't have to memorize it. Now, this ideal gas law is said to be valid only for ideal gases. And an ideal gas really doesn't exist because an ideal gas is something that we assume something that probably isn't true, that you have a substance that will follow all the other gas laws at every possible condition of temperature and pressure. In other words, the ideal gas law is operating under the very useful but often unrealistic assumptions of kinetic molecular theory, KMT, which we discussed in States of Matter, Part 1. The fact is, real gases often behave in ways that depart significantly from what KMT and the ideal gas law predict. And this is especially true at low temperatures. You can see here from the graphic, we have real gases deviate from the ideal. And we see that instead of straight lines that are either identical to or parallel to the line in the center for an ideal gas, we get curves. And these curves are more pronounced when we're at a really low temperature or if we're at a really high pressure. Despite these limitations, even though the ideal gas law doesn't perfectly predict the behavior of gases at all conditions, it can still be used to approximate the behavior of real gases at most conditions, which is to say the conditions that that we tend to inhabit ourselves. All of us tend to spend our life in a narrow range between the freezing and boiling points of water. And so in that range, the ideal gas law makes pretty accurate predictions without any additional math. Here we have an example where we're going to have a 0.1 liter balloon. Well, that's of course a unit of volume. It's going to be filled with 4 moles of CO2. That's going to be N. It's going to experience 1.5 atmospheres of pressure. That is P. And so we're going to ask, what is the Kelvin temperature? Well, we set it up like so. PV equals nRT, where that's 1.5 atmospheres times 0.1 liters. It's going to equal 4 moles times the ideal gas constant, 0.082, times an unknown temperature. Now, the tricky thing to remember is that the ideal gas constant is based upon units of atmosphere, liters, moles, Kelvin. That is, it's been calculated by taking 1 times 22.4 and dividing it by 1 times 273. That's why we have the number 0.082, but that is only valid for those particular units. But it also means that even if we don't show those units are in fact present for R. And therefore, in this problem, the atmospheres and the liters and the moles, they are all going to automatically cancel out. How are we going to do that? Well, to isolate temperature, we're going to divide both sides by the numbers next to T. We're going to divide both sides by 4 moles times 0.082. When we do that, of course, it completely cancels on one side, and the units cancel on the other side, and so we just do the math, and that will equal the temperature. In this case, it turns out it's 0.457 Kelvin. Not 0, which would be absolute 0, but less than 1, a very chilly number indeed. In another example, we're going to have a balloon with a volume of 0.4 liters filled with 8 moles of nitrogen at 200 Kelvin. And we want to know what the Kelvin pressure is. So, unknown pressure times the volume of 0.4 liters equals 8 moles times 0.082 times 200 Kelvin. We want to isolate pressure, the pressure before, so we're going to divide both sides by 0.4 liters. And when we do that, well, of course, one side will completely cancel out, and we'll do the math, and the units will cancel out, and our answer will be in the unit of the atmosphere. It'll be 328 atmospheres. Let's now turn our attention to the kind of problem that the ideal gas law can handle that the other simpler gas laws cannot. What happens if you know the pressure, the volume, and the temperature? Can you actually get an estimate of how many moles of the gas are present? Well, let's see. We have a 0.5 liter container. That's a volume. It's going to be filled with oxygen gas at 5 atmospheres of pressure and a temperature of 273 Kelvin. How many moles? So we set it up like so. We have 5 atmospheres of pressure times 0.5 liters of the volume. It's going to equal an unknown number of moles times the ideal gas law constant times the temperature in Kelvin, which is 273. Now we want to get rid of everything next to N. Those things are obnoxious, and so we're actually going to divide both sides by 0.082 times 273. Now of interest here is since we're dividing by the universal gas constant, that means that the units are flipped. Instead of atmosphere, liters, moles, Kelvin, well, it's actually moles, Kelvin, atmosphere, liters. And so we can cancel everything out on the opposite side. And we do the math, and when we get done, we discover it's 0.112 moles of oxygen. Now that may not look like a very large number, but please remember that a mole is actually our name, a stand-in for a very large number, which is Avogadro's number. 6.02 times 10 to the 23rd. A 6, a 0, 2, followed by 21 more zeros. It's actually very large. And so 0.1112 moles of that is actually a pretty large number. It's about 6 to the 22nd power molecules of oxygen gas.